Hello, Calculus BC students, Mr. Lee here again, and I wanted to go ahead and cover pretty much the last few things we need to know with regards to polar coordinates and polar equations and polar graphs. All right, so I know in this example when I printed out the notes for you guys or even when I posted them, it's pretty hard to see the cardioid that is in this graph, but there it is. I went ahead and darkened it for you so that you can kind of understand what's going on here. So let's see what we've got. So it says over here, find the area of the region common to the two regions bounded by the following curves here. So like I said, this is the last that we need to know. And in the first video having to do with this topic is we went ahead and differentiated and found slopes of tangent lines and so on and so forth. In the second video, we found areas between curves. And in this video, now we're going to find areas between two different curves. So in order to solve some of these problems, it's going to be very tricky, especially when we have to come up with the bounds just like with last time. But the other tricky part about this is knowing whether we're going to add two integrals together or subtract two integrals together. And I made sure to give you guys an example of each type of scenario. But before I get into that, I do kind of want to, revisit the idea of finding the area between curves. This circle is not centered at all, but that's okay. I forgive myself. Hopefully you do too. So here we have theta. Everything is obviously in terms of theta. If I'm just going to revisit the idea that if let's say I was interested in finding the area of this region of a circle, for example. Again, I'm no longer finding the area with between like 2 points on the x-axis. Now it's between two angles. So again, I have to think about, okay, well, I need to know where this curve, where we start with this curve. So I'm going to start at this angle theta, probably an angle of 0, and I'm going to go ahead and calculate a bunch of little tiny sectors of a circle all the way up until there. So you can almost think of it as like a guy with like standing right here in the center, and he's kind of pointing his flashlight, and wherever his flashlight is pointing to at that part of the wall, he's pretty much just kind of like, going through and pointing the flashlight across there, and it's just sort of like in him standing in one location, and then all of those little areas are adding up to give us the area of that polar region. Now sometimes it's a little bit more involved. Like for example, you're going to see like with this circle, right? I'm going to have like a circle kind of like on this half of the graph. So if I wanted to know, for example, the area of this region of the circle right there, well, again, here's the guy with his flashlight, and he's starting over here, like whatever this angle is, and he's just kind of like, again, shining his flashlight along the edge of that circle, and then that's how we're pretty much finding the area. And whatever angle this is and whatever angle that is, it's between those two angles that we figure out the angle of that area of that region. Okay, so I kind of want you to keep that in mind when we're answering this question. So either way, let's just kind of get back into it. So they were nice enough to tell us which equation is the circle, which equation is the cardioid. I'm not sure if that's always going to be the case, but we'll just kind of practice as we go. So anyway, so it says find the area of the region common to the two regions bounded. So essentially, and I'll see if I can maybe use a different color here. Let's see if my red pen works. So the region bounded between these two curves is kind of referring to like this region right there. Okay. So this is what we're trying to figure out. And if you notice, this is pretty symmetrical down the middle. The area above this axis right there is the same as the area below that axis. So you're going to see here that it's going to be a lot more convenient to go ahead and like figure out like our different areas between bounds, and then at the end just multiply it by 2 to kind of get the other side. We kind of did the same thing. Remember when we were doing the rose petal example in the previous video? Like we had our I don't even know how to draw these. Well, whatever, you get it. The rose petal problem. And they said find the area of one rose petal. If we just found the area of half of a rose petal, just multiply it by 2, and that gives you the answer of the whole thing. So that's what I mean. Like you got to be strategic with how you approach these problems. So anyways, I'm just going to go ahead and look at this. And again, here's my guy with his flashlight, kind of standing here at the pole, and he's kind of shining his light across this way, like that. So I wish I can, let me get some different colors here. That way we can kind of visually, I think a blue and green would be helpful. Maybe green and purple. Yeah, there we go. Green and purple. Those are gonna be the two colors. So let's start with the purple. So I'm gonna go ahead, and this guy, he's starting his flashlight, and you notice how, like, if I just kind of look at this area over here, that area is really only utilizing the circle part of the graph there. I'm not even using the cardioid there. So, and then once I get to this point of intersection right there, I'm choosing my words carefully here. Once I get to that point of intersection, he's kind of like, almost like switching his flashlight. I don't know if this analogy is even that helpful, but whatever. He's switching his flashlight, and now it's only pointing at the cardioid, right? So we're kind of getting somewhere here. Essentially, I'm going to go ahead and just kind of integrate between two angles for just the circle to get this area right there. And then I'll multiply it by 2 because that's going to be symmetrical to that part of the area. And then I'm going to go ahead and create another integral from whatever this angle is to this angle. And I'm going to integrate from here to here of just the cardioid. And that's going to give me the other half of the other part of the area. And then I'll multiply this by 2 to get this part right there. And that's essentially what we're going to do. So okay, well, let's kind of think about this for a second. So first of all, where is this whole curve even starting off, right? And I don't know if you remember from the last video, if we're only looking at the circle equation. So let me go ahead and look at the circle, right? So I know that my radius is equal to -6 cosine of theta. So if you think about the starting point, well, doesn't that have a radius of 0? So if we set this equal to 0, that's going to pretty much tell us kind of, a couple of ideas of what the starting point could be. So if I think about this, I divide both sides by 6. So really the cosine of theta is just equal to 0. And we know that the cosine of theta is 0 at, let's see, if I think about my unit circle, 0, 1 is up here. That's the cosine. So pi over 2 would be an answer. 3 pi over 2 would be another answer. And even though this graph is kind of giving it away, I'm just going to pretend like I'm not even seeing that. So I know that pi over 2 and 3 pi over 2, I think it's most likely going to start at pi over 2 and then kind of, every time you input an angle into this, it's going to bring you around the whole circle. And once you finally put in 3 pi over 2, it's going to bring you to the end of that circle. So I'm just going to go with pi over 2 is my beginning point to find the area of that circle. Okay. So then now we got to go and say, okay, well, it's going to start at pi over 2, and then as we keep plugging in thetas, what theta will it be at this point right there? So, well, you'll notice that you do this point is the intersection of the circle and the cardioid equation. So I think the best thing to do when you want to find the value at an intersection point is you set the two equations equal to each other. So that's what I'm going to do. So -6 cosine of theta is equal to 2 minus 2 cosine of theta. Oh boy, now we have got to do some algebra here. So I'm going to add 6 theta to the other side, so that'll be 0 is equal to 2 plus 4 cosine of theta. And then if I go ahead and I subtract 2 divided by 4, then cosine of theta will be -1/2, right? And so I got to think about, well, I'm going to think about my unit circle. Cosine of what angle gives me -1/2, so I know -1/2 will be kind of like in here, so that'll be some kind of pi over 3. So in this region, it's going to be theta equals 2 pi over 3, and down here, it'll be 4 pi over 3. All right, I promise I was not even looking at these. I'm pretty good with my unit circle. But anyways, I am pretty good. No, not really. But whatever. I got it eventually. So I know that it's going to start at pi over 2, and the likely angle that it's the next one is going to be all the way up until 2 pi over 3. So right there, I just figured out what my lower and upper bounds are. So let's kind of figure out that, so for this area in purple, you know what, just to show the connection and some exemplary teaching, I'm going to use purple to represent that area. So it's going to be the integral from pi over 2 all the way up until 2 pi over 3, right? And again, remember, if you want to do area of a bunch of sectors, it's going to be 1/2 times our radius, so -6 cosine of theta, all of this squared d theta, right? So that gives us the area of this region, but don't forget, you also can't ignore the area below that, so let's just double this, so times 2, right? Kind of went almost off my paper there. So that gives us the area of that region right there. Awesome. So now let's figure out, so we know that starting at this point, this is like 2 pi over 3. And now we're going to go ahead and say, okay, well, where is this? And is it even in the graph there? Where is it? It doesn't tell you the length of that whole cardioid, but it's supposed to say 4. Double check somewhere else. Oh, yeah. It's really hard to see, but hold on. There are supposed to be 1, 2, 3, 4 tick marks there. So this is a distance of 4. Sorry about that. I'm going to double check the problem sets and make sure that they're pretty clear to see what the radiuses are. But essentially, when we want to figure out the area of this green region right there, well, I'm going to go ahead and I know I'm going to start at 2 pi over 3, but I don't know what theta this is. Now, I'm sure most of us would guess that this theta is going to be at pi, right? But if you're not 100% sure, and sometimes it's not that obvious, what you can do to double check is you can go ahead and say, well, this cardioid is going to have a radius of 2 when I plug in like whatever theta this is. So, not a radius of 2, I'm sorry, a radius of 4, because this is a radius of 4. So that's what we can do to pretty much figure out what theta that is. So we can do 4 is equal to 2 minus 2 cosine of theta. I'll subtract 2, and that'll be 2 equals -2 cosine of theta. So then cosine of theta was going to equal -1, and guess what angle gives you? Guess what angle that if you plugged it into the cosine will give you -1? It would be pi. So there you go. So you know that from 2 pi over 3 all the way until pi, that gives you the area of this green region. So for my exemplary teaching, I'm going to use green to represent that integral. It's going to be from 2 pi over 3 all the way up until pi. This time we're going to do, the radius is the cardioid, so it's going to be 2 minus 2 cosine of theta squared. D theta, don't forget the 1/2, right? Because that's the area of all of your sectors. But then again, we can't ignore the other half of this, right? So if we doubled this result, that will give us the area of the bottom part. So times 2. And there you go. So now if I went ahead and set up my integral, the area of the region is going to be the 2 and 1/2 cancel. So it'll just be the integral from pi over 2 to 2 pi over 3 of -6 cosine of theta squared d theta, plus, I hope I don't run out of space, the integral from 2 pi over 3 all the way up until pi of 2 minus 2 cosine of theta squared d theta. All right, so that's going to be the setup of my integral. And again, you are going to be expected sometimes to be able to do this by hand, and you know, with this one, I'm probably going to have to like expand this out and FOIL and do a whole bunch of things to figure out what that is, but I trust you guys to do it. Probably just a couple of reminders. You know, you have the cosine squared of theta is equal to 1. Oh, wow, I almost forgot. Is it 1 minus or 1 plus? Yeah, it was 1. I'm pretty sure it was plus. Cosine of 2 theta divided by 2, and then we know that the sine squared of theta is equal to 1 minus cosine of 2 theta divided by 2, right? Even I forget sometimes, but that's why we practice, and that's why you guys have to practice this as well. So anyways, that's how we do this example. All right, so again, we have this is one of the examples where you have different areas that you're solving for, and you're adding the two integrals together. Okay, sorry for the awkward transition in clips, but someone rang the doorbell. I stumbled upon my words. I just figured I'd start over again. But anyway, so here for example 6, it says find the area of a region between two curves. and find the area that is inside of pretty much this outside curve, the 3 plus 2 sine of theta, and outside the circle. So here's our circle with a radius of 2. And then graph these two curves that is, the graph of these two curves is shown on the right. So this is going to be an example where we're going to subtract two different integrals. And just to kind of give you guys more of the visual of what's going on here, I'll just kind of show you. So first of all, we know that this outside circle is represented by that, whatever that is. I don't even know if it's a cardioid or a limacon or whatever. So 3 plus 2 sine of theta. Okay, so here's the thing. Again, I highly recommend that you think about like that man with a flashlight kind of standing in the center there. If he's kind of pointing his flashlight, he's probably going to start pointing his flashlight down there and just kind of go around the circle, not the circle, the limacon or the car, whatever that is. The flashlight around there. Please don't judge me for that. I don't remember most of the polar graphs, but I do understand the calculus. So anyways, so he's pointing his flashlight and kind of like touching this part of the graph all around. Now the thing is, it would be nice if that was the only, if all of this was the area that they're interested in. But essentially, they're only interested in the area between these two curves, not necessarily this part that's like inside of the circle. So what we're eventually going to have to do is we're going to have to, get a different man with a different flashlight, but pointing at a different wall. This wall being the circle, right? Figure out what that area is and then subtract the 2 to only get the area of the region we're interested in. So that's pretty much what we're going to be doing here. So if we go ahead and figure out the area of what's in blue and then subtract the area of what's in red, then that pretty much gives us the area that we want. So let's see. First of all, let's start thinking about first what the area of that the blue region is, right? So I'll use my blue pen for that. So again, I'm going to start over here at the center, and I'm going to go ahead and come out to that region right there. Okay, so I'm going to go ahead and say, okay, well, what are these two intersection points? So I'll have, let's see, to figure out, well, any intersection point, I'm going to set the two equations equal to each other. So what I'll do is, of course that happens in the video, drop my pen. So I'm going to go ahead and set these two equal to each other. So I'm going to have 3 plus 2 sine of theta is equal to 2. And then I'm going to go ahead and subtract 3 from both sides. So I'm going to subtract 3. I don't know why I'm showing all of this. I could have just said that sine of theta is equal to negative 1/2, because that's negative 1 divided by 2. I think you guys are smart enough for that. So now from here we got to think about, well, our theta is going to be, let's see, sine of what gives you negative 1/2. So if I think about just what's in the unit circle, it's going to be 7 pi over 6, right? Because if I think about my unit circle, sine of negative 1/2, that's a y value of negative 1/2. That's like over here and over there, right? So that's like 7 pi over 6, and that's 11 pi over 6. That doesn't really help us much, right? Because if you think about it, like, how are we going to, because I mean, we're almost kind of like starting here, right? How are we going to start at 11 pi over 6? Because isn't that like, to get to 11 pi over 6 and like say we're starting at 0 degrees, right? Or, 0 radians. To get to 11 pi over 6, we pretty much already traveled almost the entire circle. So this is one of those tricky parts where, you kind of have to be a little bit more savvy with your trigonometry here, or your polar grid here. Because the thing is, it doesn't make sense to start at 11 pi over 6. That's almost an entire revolution of the circle. So what we have to start thinking about, and hopefully this doesn't make your heads explode, but essentially you got to think, well, what's the equivalent of 11 pi over 6? That would be a pretty feasible starting point. And honestly, the equivalent to that would be negative pi over 6. That makes a lot more sense as being our starting point. So we're not starting at 0, we're actually starting just a little bit before 0 and starting at negative pi over 6. Okay? So that's what we're going to do. So I know that I have negative pi. So this, instead of 11 pi over 6, we're going to use negative pi over 6. And it doesn't make sense to start over here. Because then if we start over here and kind of continue on this way, then we're finding the area of this region, and that's not what we're interested in. We're interested in the region this way. So we're actually going to start from negative pi over 6. And here's the thing. We could make that our lower bound of the integral, because essentially what we're going to do is we're going to find, where's my blue? We're going to find the integral from negative pi over 6, right, to some upper bound. And it's 1/2 times the radius squared. And it's going to be the radius of this function right there. So 3 plus 2 sine of theta squared. Okay, so yeah, d theta. Okay, but the thing is, if to figure out what our upper bound is, sure, we can leave it like that and say that our upper bound is going to be, because I know that this right there is 7 pi over 6, right? So we can say that our upper bound is 7 pi over 6, but this is one of those situations where it's pretty symmetrical if I just kind of stopped all the way up here, right? So I'll show you both answers, and maybe I'll show you with the calculator. Maybe I'll leave that for you guys in the calculator, but it'll actually end up being the same thing. Now, if I start at negative pi over 6, I can go ahead and I'm flashing my light all the way around, and I can actually stop right up here, right? And I'm sure most of you will guess that stopping point is pi over 2. Just to be safe, let me prove it to you, right? Proofs are always low. I was trying to come up with a good phrase, but that sucks. But anyways, so I'm going to go ahead and set this, and my radius at that point is 5 right there. Yeah, 1, 2, 3, 4, 5. So 5 is equal to 3 plus 2 sine of theta. Subtract 3 from both sides. I get 2 is equal to 2 sine of theta. So the sine of what angle gives me 1 pretty much. And guess what? It's pi over 2. So there you go. So that's my upper bound, is pi over 2. And I don't know why I switched to black. Should have made that blue. Whatever. So, and then, but the thing is, if I only find that area, like with the upper bound of pi over 2, that only represents half of that area that I'm interested in. So I'm going to have to multiply this by 2 to double all of that. Okay? So there's my area of the outside region. So, I'm pretty sure that's a limacon. So I'm just going to go ahead and say that the area of my limacon is equal to all of that. Or I'm going to say, maybe I should say like half of the limacon. Whatever, this is getting sloppy anyways. So that gives me the area of all of this region. So now I got to subtract the area of just the circle region. So that one's not too bad. It's pretty much going to be the same bounds, isn't it? So it's going to be, so the area of the half circle, I guess you can call it, is going to be equal to double times, or whatever, double the value of 1/2 of the integral from negative pi over 6 to pi over 2 of just the circle. So the circle squared, so the radius 2 squared d theta. And that's about it. So my area of the shaded region is just going to be equal to, let's see, the integral, because it's 2 times 1/2 is 1. The integral from negative pi over 6 to pi over 2 of 3 plus 2 sine of theta, all of that squared d theta, minus the integral of that half circle. So the integral from negative pi over 6 to pi over 2 of 2 squared d theta. Or you could have just said 4. Whatever, I don't know why I left it like that. Likewise, this is actually going to be the exact same thing as area shaded. I could have also done like the area of the whole thing, right? So if I did from negative pi over 6 to 7 pi over 6, it actually would have been the same thing as 1/2 the integral from negative pi over 6 to 7 pi over 6. And again, I'm not doubling it, so I have to leave the 1/2 there of that whole thing. 3 plus 2 sine of theta squared. D theta minus, and then 1/2, because I'm not doubling the area anymore. If I go from negative pi over 6 to 7 pi over 6 of 4 d theta. Both of these will give you the exact same answer. And yes, I actually did all of it. And just to double check, and just take my word for it. And if you don't believe me, then plug it in yourself and you'll see for yourself. So both of those will give you pretty much the correct area of the shaded region. So I think I made that video long enough. I'm going to go ahead and leave you guys there. And hopefully, and honestly, my recommendation, especially since the AP exam is getting closer and closer to us, I highly recommend that you work these out by hand, especially when you do the problem sets. And I'm going to be nice and I'm going to post, because I'm stealing these problem sets from a different teacher. And the teacher has beautifully worked out solutions to all of these problems. So I'm going to make sure to post those solutions for you guys so that you can kind of double check your work and see how they do it. So hopefully that was helpful. Hopefully you're not exhausted and too tired of these videos or hate me more than I am suspicious of. And then, yeah, that's about it. I'll let you guys go. Take care. Good luck. Have a good break.